Okay. See, like as I mentioned in the last class, we'll be talking of what we call as the simplex algorithm. Okay. So it's an algorithm that sort of, allows us to find or to solve any linear programming problem algebraically. Okay. So that means even if we have more than two decision variables, we'll be able to solve using this algorithm. Okay. Now, I had given you a gist of this algorithm, the logic behind this algorithm, how we move ahead, and so on and so forth. But now we'll be actually solving a problem today. Okay. Now, the thing is that there are various methods. I mean, there are various, no, I should not be saying methods because the method is only one, the simplex method, but there are various ways to present this algorithm in a tabular manner. Okay. So, like for this, I mean, the format or the presentation which is being used in this book, we would be following that for this particular semester. Okay. Now, if we study this particular paper of just linear programming problems in the next semester, then we'll have a different kind of a presentation, but the logic and the method will not change. It's just that the presentation that will change. Okay. Now, in this, one thing that we have to remember, I mean, there are certain things before we start with the tabular presentation and solving algebraically, there are certain things that we have to take care of. The first thing that we be handling here is that all our problems would be maximization types, number one, and all our constraints would be less than or equal to types. Okay, so in case you have a minimization problem, you can always convert it to a maximization problem by multiplying the objective function with -1. Okay, now, of course, all our constraints would then be less than or equal to sign. This is one thing that we would be, sort of concentrating upon only. Okay. Now, then what we'll do here is, I mean, the thing is that in our in our given linear programming problem, we have an objective function. Okay. That we know. Okay. We have a set of constraints that we know, and then we have a set of non-negativity restrictions that we know. This is how the structure looks like. Okay. Now, when we start solving this algebraically, what we'll do is we'll bring this objective function also in this set of constraints only. And we would, how I'll just tell you how, but we'll just call that set of constraints as augmented constraints. Okay, in the sense that we would augment the original set of constraints. Okay, in a way so that we are able to add, I mean, we'll just add the objective function there. Okay. So, see, basically what we are doing here is like, say, as I said, I'll take the example exercise problem. Say, if you just look at your question number 9 of this exercise, I think this is 7.4. Yes. Then the problem is optimize, but I'll start with maximize. Okay. See, the problem is maximize 6x1 plus 4x2 subject to the constraints minus x1 plus x2 less than or equal to 12, x1 plus x2 less than or equal to 24, and 2x1 plus 5x2 less than or equal to 80 with x1, x2 more than or equal to 0. Okay, so this is your problem. So this is your objective function. These are your constraints and these are your non-negativity restrictions. Now, when we are solving algebraically, every time we will not mention them because we are assuming. And I think when we discussed the one-to-one correspondence between the geometrical and the algebraic, I explained that whenever your decision variable takes up a negative value, it fails to be a feasible solution. Okay, so it's understood that our algorithm will always talk of solutions that are feasible. So basically, this non-negativity restriction will be taken care of. So we need not write it again and again. But these are my set of constraints, and this is my objective function. Okay, now as you can see, my objective function is maximization type, and all my constraints are less than or equal to types. Okay, so my first assumption that I wanted is justified. This is what I have to check initially. Okay, now the second thing is that we have to construct the set of augmented constraints. Okay, but before that, before we begin with that, what we do is that we can, sort of have these steps simultaneously, but just for your understanding. Now, if you just go back to your knowledge of linear algebra, it's like you have three equations and two variables, right? So obviously 3 minus 2, which is one variable, can be given an arbitrary value, and the others can be expressed in terms of that variable when we solve such equations. But since these are inequalities, so I'm not talking of that, right? Now, we have two decision variables, and geometrically, if you what did I like in the last class? I said we need one solution to begin with. Okay, and normally the solution to begin with is the solution which corresponds to the origin, because we know that x1 equal to 0, x2 equal to 0 will always be a feasible solution. Okay, whether it will be optimal or not, that needs to be checked, but it will always be a feasible solution. So that means it's the easiest solution to begin with. Okay, so here also, when we are beginning to solve it, when we are learning to solve it algebraically, we'll be handling this kind of, we'll be starting with this kind of a solution only. So this will be somewhat look like an initial solution. Okay, that means initially we are starting from this extreme point of origin. Okay, so when we start with x1 0, x2 0, but then when we are solving algebraically, we have to convert these inequalities into equalities. That means we have to talk of the slack variables. Okay, and not just this, if you just see, when x1 is 0, x2 is 0, what is the value of the objective function? Obviously 0. So that means that becomes the value of the objective function at this particular extreme point. Okay, so what we can do here is that, or in other words, we can say that this is my solution, one solution at which the value of the objective function is 0. Okay, now, obviously, when I want to improve this solution, when you want to improve this solution, amounts to saying that you want to move to the next extreme point. Okay, so when you want to move to the next extreme point, that means you want the value of your objective function to be more than or equal to 0. See, there are two, when you start with one particular solution, there are two options. Either this is optimal, so we end up here. If this is, the other option is that this is not optimal. So if this is not optimal, that means there is a better solution. Better solution means there is a solution that will give you a value of the objective function which is better than the existing value. And what is the existing value? 0. So we use this logic and construct the set of augmented constraints. Number one. Number two, since we have these, okay, let me write the augmented constraints first, then maybe, things will be more clear to you. So like your first constraint was minus x. Your first constraint is this only, na? Let me go back. I've forgotten. Minus x1 plus x2, yeah. Minus x1 plus x2 less than or equal to 12. X1 plus x2 less than or equal to 24. 2x1 plus 5x2 less than or equal to 80. Okay. Now I bring in another constraint, in the augmented, where I want the value of the objective function to be more than or equal to 0. Okay. So this is the extra constraint that I have brought in. That's why we are not calling it as the set of constraints. We are calling it as the set of augmented constraints. Is this clear or not? Just tell me that. And of course, you have your non-negativity restrictions, which we are not going to write again and again, as I said. Is this clear or not? That's, huh?
Ma'am,
Huh, bolo.
objective function will always be greater or equal to 0 if
Because
we
that's the initial solution we are starting with. So we want it to be either greater, if x10, x20 is optimal, that means the value of the objective function will be 0. That's why we are starting with maximization only. So for maximization problems, what is the minimum value which the objective function can take? 0. उसके बाद तो value of the objective function is bound to increase in case it is not optimal. If it is optimal, that's why we are saying greater than or equal to 0. If the current solution is optimal, that means z equal to 0 is the optimal solution, optimal value of the objective function. So it cannot improve further, but it cannot be negative, definitely, because it's a maximization problem. But if it is not optimal, that means it has to improve. So if it has to improve, that means it has to more than, see, this was your feasible region somewhere. So basically you are starting from 0 here. And if you see, if you plot the iso kind of lines, then this is how the objective function should behave. The first value to yahi aayegi na, here. And what is the value of the objective function here? Z equal to 0. If it has to improve, that means it will move in this direction. So if it moves in this direction, maybe it will be an optimal here or optimal here, depends upon the solution. But definitely this will be more than or equal to 0. So we are treating it as a constraint here, but it is actually, this constraint is related to the objective function. So as I said, this is just a presentation as explained in this book. This is not the only form of presenting the simplex table. Okay?
Okay, ma'am.
Anything else that somebody wants to ask? Because अगर ये clear नहीं हुआ तो आगे problems नहीं होंगे.
Clear, ma'am.
Okay. So, but now again, since we are solving algebraically, we still have inequalities. So we want to convert them into equalities, right? And not just this, we have one inequality of the form more than or equal to 0. And I wanted all of them to be less than or equal to types. So basically, your augmented set of constraints, still in the form of inequalities, I'm writing, should be this: minus x1 plus x2 less than or equal to 12, x1 plus x2 less than or equal to 24, 2x1 plus 5x2 less than or equal to 80. And to convert the last inequality into less than or equal to types, I just multiply by minus 1. And I get this. Is that okay? Because I want all my inequalities to be less than or equal to types. Now they are inequalities. We need to convert them into equalities. So what do? We introduce the slack variables in the constraints. But slack variables would come only in the constraints. This is not a constraint actually. This is actually a objective function. Physically, if you just look at the problem. So that means I cannot have a slack variable here. So what I'll do is, now will be the final augmented. I mean, this is just for your understanding. In the exam or when you are solving, you can write it directly. There is no issue with that. So it will be something like minus x1 plus x2. This will be my first slack variable, x3. Then x1 plus x2 plus x4, the second slack variable, equal to 24. Then 2x1 plus 5x2 plus x5 equal to 80, which is my third slack variable. And in this, instead of introducing some xi, what we do is we simply write it as plus z, which will be your value of the objective function. So z is basically nothing but 6x1 plus 4x2, which is actually your objective function. So the purpose of writing z here is, I mean, that's for just to make you understand this. I explained all these steps. Okay, so this becomes your set of augmented. Now this is your augmented set of constraints. Okay, so that means the first step, given a problem to solve, the first step that you have to do is, number one, ensure your objective function is maximization types. Okay. Number two, ensure that all your constraints are less than or equal to types. And number three, just write this augmented set of constraints. You can do away with these previous steps. This was just for to make you understand. We'll directly write this as my set of augmented constraints. Is this okay? So this is your step one, where you write your augmented constraints. Is this okay or not? And of course, when you have augmented constraints, so everything x1, x2, x3, x4, x5, z, they're all more than or equal to 0. Okay, now you understand, because I want my z also to be more than or equal to 0. So that's why I want my constraint to be more than or equal to 0. Is this clear or not?
Yes.
Okay. Now, in the step 2, we'll move to the tabular format. Okay. So in my step 2, I will assume that x1 equal to 0 and x2 equal to 0 is the solution. Okay. Now we make a table, which we call as the simplex table, which will be, in this case, the initial simplex table. Okay. Now this you have to understand carefully. In this, what we'll do is, we'll write all the variables here. x1, x2 were my decision variables. x3, x4, x5 were my slack variables, and my z. Okay. And this will be the right hand side of the equations, the constraint sets. Okay. Now what we'll do is, we'll make entries in this table. The block on the left hand side of this line would be the coefficients. Okay. Now, if you just look at the first constraint, what is the coefficient of x1 in the first constraint? Now look at the augmented constraints. Okay. So what is the coefficient of x1?
The minus one.
Minus 1. Coefficient of x2?
One.
1,
Coefficient of x3?
1,
One.
Coefficient of x4?
0,
x5?
0,
Zero.
Z? Is
0,
there any z in the first constraint?
No,
no,
ma'am.
So what is the coefficient? 0. And what is the right hand side of the first constraint?
12.
12,
12. So this becomes your first row. Fine. Now the second row. What will that be?
Ma'am, 1101.
1, 1, 0, 1,
0, 0.
0, 0, and then
24.
24. Right. Then the third one, 2,
250010.
0, and then 80. Right. Now, the last, which is corresponding to the constraint, is still left. So what we'll do is, we won't write it along with it, because that is actually not a constraint. So we'll draw a line here and then write the last row, which is actually the z row. Okay. Now, what is the coefficient of x1 in this?
Minus 6.
Minus 4, 0, 0, x3, x4, yeah, 0 and 1. and the value of z is 0. Why? Because when x1 is 0, x2 is 0, the value of z is 0. Okay, so this is your initial simplex table. Is this clear?
Yes, ma'am.
Okay. Now, to improve, see, now we have to talk of two things. Number one, the optimality criteria, and number two, the improvement criteria. दो चीजें करनी है ना हमें, because we have to check whether the current solution is optimal or not. If it is optimal, we stop. If it is not, then we move over to the next better solution. Okay, or in a way, we move over to the next solution which will give us a better value of z than the one that we have at a present state. Okay, so basically we need to move over to a solution which will give us an improved solution of the objective function. Okay, is that okay? Is that okay or not?
Yes.
Okay, now for the optimality criteria, see what if you just look at this solution and the equations that you have with you, when you put x1 equal to 0, x2 equal to 0, right? What does the first constraint tell you? When x1 is 0, x2 is 0.
X3 equal 12.
No, okay, yeah, that's perfectly right. Maybe I'll rephrase my question. I say when x1 is 0, x2 is 0, and it's just a rough work that I'm doing here for you to understand. When x1 is 0, x2 is 0, what is the value of the other variables here? I mean, what will be the value of x3? What will be the value of x4? What will be the value of x5? And what will be the value of z? Z तो 0 हो गया, fine. So x3 you said is 12, है ना? What about x4?
24.
24. And x5?
80.
80. So basically this is the solution that you have, right? And this corresponds to which point geometrically? The origin, x10,
Or
x20. ठीक है ना? So when we move over to the next point, so that means we are trying to move to the next intersection point. अब वो intersection point दो constraints का भी हो सकता है. It can be an intersection point of some axis and one constraint. If it's a point on the x1 axis, so obviously it's an intersection between the x1 axis and some constraint, or an intersection of the x2 axis with some constraint, or an intersection between any two constraints. So that means we have to move on. So when you move on, it means that from x1 and x2, one of the variable is non-zero. यही मतलब हुआ ना, कोई और variable value लेगा ना इसका. मतलब in a way what will happen is that this x1 will either, I will not say x1, either x1 or x2 will become non-zero and some another variable will become 0. Are you getting my point? See, as I said again, अब इसको फिर से अच्छे से समझो. Either this solution is optimal. Okay, let us say, okay, let's talk of the optimality criteria right now. Okay, to remember the rule, just remember that if I say optimality criteria, basically this means that if a negative, see, if you have a negative coefficient in the last row, which you have written at the end of the table, okay, which is your last row? This row, this one. I mean, sorry, not Z here. This row. If you have a negative value, if you have a negative coefficient present here, that means the current solution is not optimal. Okay, so that means for the current solution to be optimal, what do you want? All these values to be either 0 or positive. We don't want them to be negative. Is this clear? So we say that a negative coefficient in the last, or the this can be called as the z row also. In some books you will see that this row is called as the z row or the objective function row, whatever you want to call it. Okay, so any negative coefficient present here indicates that the current solution is not in the last row indicates that the current solution is not optimal. Okay, now if it is not optimal, it means that the value of the objective function can be improved. Okay, now see, come back to our linear algebra. Now, after augmenting and converting it into, say, equations, just forget about the last row here. In the constraint set, how many equations do you have now? The constraints, how many equations are there?
3,
Three. And how many variables?
5,
Five. So how many variables can be arbitrarily put to 0?
2,
Two. Okay, so that means we start with this choice of two. Like in the last class we looked at all the possible combinations. थी ना 5C2 हमारे पास values आनी चाहिए where which can be put equal to 0, right? But now we started with this. Okay, let's call them as independent because we are arbitrarily putting them as 0 and we are expressing the remaining in terms of these two. So basically they are independent, right? Now the thing is that if I make a choice of putting x1 and x2 equal to 0, then because of the presence of -6 and -4 in the last row, this solution is not optimal. It can be improved. Now, if it can be improved, then that means either x1 or x2 has to be non-zero because I cannot change the number of variables that can be put to 0. They have to be 2 because I have five variables and 3 equations. Okay, it's just that the variables which we are putting equal to 0 can change. So definitely this means that either x1 or x2 will become non-zero, and out of x3, x4 and x5, one of them will become 0. Which one? We are not sure as yet. But definitely one out of these will become 0 and one out of these two will become non-zero. So basically it amounts to saying that one out of x1 and x2 will become dependent and one out of x3, x4 and xy will become independent. Okay, now the thing is that now we have to choose which variable, or in a way we call them, see, in a way we say that they are forming the basis. So we have to choose which variable will leave the basis and which variable will enter the basis. But number of basis vectors will not change. They will still remain 2 because our independent variables will always be 2. Okay. So in other words, again, I'm repeating this. Now we have to choose, one independent variable which will become dependent and one dependent variable which will become independent in such a manner that we reach the optimal solution in minimum number of steps, or we attain optimality at the earliest. This is the objective. Okay, so that means when we choose, so basically we are choosing one entering variable and we are choosing one leaving variable. So entering variable kaun sa hoga? The one which would change its nature from dependent to independent. And leaving variable kaun sa hoga? The variable which will change its nature from independent to dependent. Is this clear?
Yes, ma'am.
Right? Not only this, when we choose a variable to enter, or we can say when we choose a variable which will become independent, then it has to be chosen in such a manner that the solution still remains feasible. See, if you remember the last class where we looked at all the possible combinations and then we evaluated the things, we observed that out of all the possible combinations, not all the solutions were feasible, right? We came across solutions where one of the variable was taking a negative value. So it is not to be considered. So definitely, it's like saying that we will not move to an extreme point which does not belong to the feasible region. So we have to choose the variables in this manner. And the algorithm, the method, the rule that exists, how to choose the entering and how to choose the leaving, is so good that you will never end up at a solution which is not feasible, and you will attain the optimality in minimum number of steps. Okay, so basically the step 3 now, this is the optimality criteria. We just check whether, if you want to call it, okay, let's call it step 3. We check whether the current solution is optimal or not. Now, in our problem, because I have two negative coefficients, so definitely the current solution is not optimal. So we have to move ahead. Okay, so we move to step number 4, which is your to decide which variable will leave the basis. Just a minute, girls. Okay, now we'll first of all decide which variable will leave. Leave ka matlab either x1 or x2 will become non-zero. Okay, so that will be my leaving variable, one which becomes non-zero. Uske liye the rule says, we just look at the last row, which is your z row. Okay, so it says that the most negative, just look at this, most negative value, the variable which corresponds to the most negative value in the z row will be the variable which will become non-zero or which will leave. Is this clear? Remember, most negative, okay, or that means absolute value maximum but with a negative sign, right? So which one is that in your table?
X1.
-6. Okay, -6 hai na,
Yes,
right?
ma'am.
So this corresponds to what? X1. So that means x1 leaves the basis, or we say that x1 becomes non-zero. Okay? So that means x1, basically this amounts to saying that x1 would improve the current objective value. What was the current objective value? 0. Okay, so once x1 becomes non-zero, then the current objective value will improve. That means what? It will become more than 0. What? That we'll see later on. But definitely we have decided upon that x1 will become non-zero. So basically what we do is we mark this column then. Okay, this column, right? Now, if you just see, then as I mentioned, this x3, x4, x5. So basically, this corresponds to x3, this corresponds to x4, and this corresponds to x5. Okay. So basically, what is happening is that the last row is deciding which variable will become non-zero, and the last column will decide which variable will become 0 out of x3. See, we had just these 5 variables with us, out of which 2 can be 0. We started with the choice of x1 and x2 to be 0. But now we have come to a conclusion that x1 should be non-zero. So if x1 has to be non-zero, that means either x3 or x4 or x5, they have to be 0, because x2 will still remain to be 0 at a level 0, right? So x3, x4, x5, one of them out of these three has to be 0. But which one, that needs to be decided. So that becomes your entering criteria, okay? Or which we exiting variable, in a way, this step 4 is the criteria for the exiting variable, which variable is leaving or which variable is becoming non-zero. Step number 5 will be your entering criteria, which variable will enter. Now, for this, what we do is we compute ratios, right? Ratios corresponding to, what we'll do is this column. Now, just understand this properly now, because this is to be understood clearly. This column and this column, okay? But the ratios have to be computed only for those values which are positive here. Mind you, even if it's 0, it is not to be considered. Like if you say -1, then we will not consider the ratio here. So which amounts to saying that x3 will not become 0, never, because the corresponding term here is negative. So because of this presence of negative term here, if I choose x3 as the entering variable, it will end up with a infeasible solution. Non-negativity restrictions would be violated there. So that's why we'll not consider this. Okay, not even 0. Okay, so we just compute the ratios of this value 24 upon 1, then 80 upon 2. Okay, so the ratios that you are computing here, like corresponding to x4, it's going to be 24 upon 1, and corresponding to x5, it's going to be 80 upon 2, which is 40. Now, out of these ratios that we have computed, we choose the minimum. Okay, this ratio is how much? 24, and this ratio is 40. So out of all the three ratios that you have computed, we choose the minimum. Okay, so if you want, I mean, if there is space, I have already messed it up. You can write the ratios here along with it, so that clearly you know, which is the minimum. Now, in this case, which is the minimum ratio? 24, right? So basically, this amounts to saying that x4 enters. Okay, so x4 enters means what? x4 becomes 0. So x1 becomes non-zero and x4 becomes 0. Is this clear?
Yes, ma'am.
Right? So x4 enters, x1 leaves. I mean, you can use any language you want, right? So you have a leaving variable with you, you have an entering variable with you. Now comes the next step, which is called as, what is the step number 6, which we call as pivoting. Pivoting means now rewriting the table with the new set of variables. Okay, now in this case, what is happening? Your x2 is 0 and your x4 is 0, not x1 and x2. Now you have redefined your variables, right? So what we do is, now we will make use of what we call as the elementary operations in matrices. Okay, now just see, come back to this table. It's like, see, if you just see with x1 0, x2 0, look at the values, the entries here. Do you see an identity matrix somewhere?
Yes, ma'am. Corresponding to x3, x4, and x5.
Corresponding to x3, x4, and x5. Look at the order here also, x3, x4, x5. This was the first constraint, second constraint, third constraint. So corresponding to x3, you have this 0, 1, 0, 0, 0, 1. Okay. Now what is happening? But it was not corresponding to x1 and x2, right? So basically, this means that whichever variable is non-zero here, okay, will have a corresponding identity matrix somewhere here. Okay. Now what is happening? Your x1 is leaving, or x1 is becoming non-zero, but x4 is becoming 0, right? So basically, x1 and x4 are interchanging their places, right? So that means the column that we had for x4 now should become the column for x1, because they are interchanging places now. So basically, what should we have? Instead of this, I must have 0, 1, 0. So not only this, if you just see, how do you do that? If you just see the row corresponding to this x4, then what is the element in present at the intersection of the leaving variable and the entering variable? This element is called as the pivot element or the key element, because this is going to define how we are redefining our elementary operations now. Now it's all, the way you do with matrices, the same procedure we are going to do. Okay. So it's like we'll get a new table now, but then in the new table, what we have to do is corresponding to x1, I must have 0, 1, 0. So corresponding to this, I must make some elementary operations. So what should be the elementary operations here? My R1 should change to R1 plus R2. This is already 1, so I need not divide that row. So my R1 should change to R1 plus R2. My R3 should change to R3 minus 2R2. यही होएगा ना, तभी तो ये 0 बनेगा. We have to make this and this 0. And whatever operations you perform on this, the same operations have to be performed here on the right hand side. That's what the rule says. That's why we are just performing the row operations. So it's like a prefactor. So you're performing operations on a prefactor, so they have to be performed on the product also. It's like AX equal to B. So if you're performing operations on A, you have to perform operations on B also. And the same operations we perform on the Z row as well. We have to make this 0. So if you just see, for elements, for variables which were non-zero, had a 0 value here. Okay. So what we are going to do is going to perform 3 elementary operations, which is called as pivoting. We are going to change our R1 to R1 plus R2. We are going to change R3 to R3 minus 2R2. And we are going to change R4 to R4 plus 6R2. Okay. And then rewrite your table. X1, X2, X3, X4, X5. And I had a Z here, and this will be my right hand side. Now you write your R2 first because it did not change. Okay. So what was your R2? 1, 1, 0, 1, 0, 0, and 24. Because R2 we were not changing. Now what will be your new R1? Quickly change R1 to R1 plus R2 now.
मैम 0 to 1 0
1
0
1 0 0.
क्या 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 क्या?
मैम 0 to
हाँ 0
1 1
1
1 1
1
0
0
0
36.
36.
Correct. What about R3? You're changing R3 to R3 minus 2R2. Oh God. Quickly.
Ma'am, 0, 3, 0,
Just a minute.
-2,
0, 3, 0, minus
-2, 1,
2,
0,
1,
no,
0,
32.
32. And the last row?
Ma'am, 0, 2, 0, 6, 0.
Just a minute.
Yes, ma'am.
हाँ, बोलो फिर से.
Ma'am,
0,
0, 2,
2,
0,
0,
6, 0, 1,
6, 0, 1. And
1,
here,
144.
144. Right? Now see, this is your new table now. So basically now we have to repeat the steps. That means repeat your optimality criteria. What was the optimality criteria? If a negative coefficient is present here, do you get a negative coefficient here?
No, ma'am.
That means the current solution is optimal. No improvement is possible. Okay. Now just understand this. The first row corresponded to x3. ठीक है ना? अब second row में क्या हो गया था? Initially it was x4, but x4 has replaced its position with x1, right? So this is x1. And what was this? x5. Are you getting the point here? So that means the current solution which you are now at is your optimal solution. The only problem is how to read this solution. So if you just look at this value, this is your maximum value of z. This is your optimal z. So if you just from this table only, you see what you are getting here is x1 equal to 24. ठीक है, यहां से आया, right? x2 was 0. See, you had 5 variables: x1, x2, x3, x4, and x5. You had put x2 and x4 as 0. So they'll remain as 0, right? But for x1, x3, and x5, they will come from the right hand side of this table. Okay. So x1, 24, x3, 36, and x5, 32. And what is the maximum z that you get? 144. But it's just that these three variables are not physical variables. So if you solve it geometrically, you will get the optimal at this with maximum z equal to 144. Is this okay?